Welcome to lecture 27. In this lecture, we're going to talk more about inductors. We're going to talk about the potential induced when we change a current. We're also going to talk about energy storage in inductors. The next question we'll ask now is, what is the potential difference across the ends of an inductor if the current through the inductor is changing? So far, what we've covered is also known as mutual inductance. If we have two loops, each carrying a current, and we change one of the two currents, that induces a magnetic field and a current and a potential difference in the other loop. So this effect can also happen in a single element with changing current, such as we have here on the slide. This is called self-inductance, and this is where the definition of inductance actually comes from. So our definition of inductance was L equals the number of turns times the magnetic flux divided by current. Okay, so how does our induced potential fit in here? So let's start by saying we have a solenoid, such as drawn in the picture, and let's say our current comes in on the left end. So here's our current coming in now, comes in, around, behind, and back, and up in the front. Okay, it's a little bit hard to draw 3D. Hopefully you're kind of getting the idea. So the current is flowing around this way. When we have a solenoid with this direction of current flow, what we know is that we'll get a magnetic field that points from right to left. That magnetic field will be constant inside the solenoid and it'll be zero outside the solenoid. So this is not new material so far. So this is the magnetic field, and that happens because we have a current I flowing in the solenoid. I'll write shorthand B from I. So there's a picture of what we've got going on. We know that if the current is constant and the resistance is zero, the potential difference across the two ends is going to be zero. Now, what if we don't have the current constant? What if we change the current? So let's say we increase the current I. Now let's ask what happens. So if we increase the current I, that's going to strengthen the magnetic field that points left, just from the right-hand rule. If we strengthen the magnetic field that points left, we're going to induce a new magnetic field that opposes that change. Draw that one in a slightly darker blue. You know what? That one's not really dark enough. I don't know if I can erase it. Yeah, I'll erase it. Grab a darker blue. So our induced magnetic field there, that pops a little bit more. So our induced magnetic field is going to point to the right. Okay, so we increase the current I. That induces a magnetic field to the left, to the right, induces B to oppose that change. And then what happens? If we have an induced magnetic field pointing to the right, that's going to induce a new current. And that current is going to flow in the opposite direction. So our induced current is going to come up and down around this way. That induced current is going to oppose the original current because we want to oppose that original magnetic field. So that darker green line is the new induced current. So we get an induced current which is opposite. Okay, so what does that induced current do? Let's make sure we understand what's happening here. So the induced current will move positive charge because remember, current is just the flow of positive charge. So the induced current moves positive charge towards the left end of the inductor. And that's just because that's what current is. What does it mean? And this is like what we discussed with Faraday's effect. Magnetic forces made charges flow. The separation of charge led to a potential difference. So if we get our positive charge built up on the left end, it means the left end is at a high potential. And the right end at lower potential. Let's label that in our diagram. So our left end is going to be high potential. I meant to do that in red so it would stand out a bit more. And our right end is at lower potential. That means there's going to be a potential difference between the two ends, delta V across the inductor. Our high end we would normally call the positive end, the low end we would call the negative end. Okay, so the potential difference across the two ends we'll call delta VL equals the potential difference across the inductor. And that's an induced potential difference because it only happens because we changed the original current. Let's fit in Faraday's law here. So Faraday's law says that the induced potential, in this case we've labeled that delta V for the inductor, is equal to minus d phi, the change in magnetic flux, by dt, so with respect to time. So the negative sign says that it opposes the change. And we'll remember here that our magnetic flux is related to inductance because inductance is the flux divided by the current. That's the flux. Yeah, that's our magnetic flux. Okay, so that means that our induced potential delta V is equal to minus d by dt of L times I. L is a constant because it depends on the inductor itself. We wrote that equation on a previous slide. Depends on the radius and the length and the number of coils. So that leaves us with delta VL, the potential difference across the two ends of the inductor, is minus L times di by dt. The size of the potential difference depends on the inductance and it depends on how the current is changing. So if we increase the current, then our change in current with respect to time is positive. di dt is positive, and that means then that the induced potential will decrease when you move in the same direction as I. So the induced potential decreases in the direction of I. A little bit of shorthand there, but hopefully that makes sense. Since we just talked about what happens when the current increases, I think a natural next question is what happens if the current decreases? So let's start with our same setup. Our current comes in at this end. So there's our current I. So it comes around, goes down in the back, up in the front. So there's our current. That current makes a magnetic field that points from the right end to the left end. That's the magnetic field made by the existing current in the solenoid, magnetic field B. If we decrease that current, that makes the magnetic field, which points to the left, makes it smaller. Lenz's law says we're going to induce a new magnetic field that maintains that magnetic field. So if we make it smaller, the new induced field is going to be in the same direction, B induced, to maintain the field. If that's our B induced, then our induced current is going to be in the same direction as the original current. So the induced current will also be in this direction. So there's the direction of our I induced. And that's what happens if we decrease I. Okay, what does that mean about the charge and the change in potential? Remember, the charge, positive charge, is moving positive charge is the same as current. So if the current flows from the left end towards the right end, positive charge is going to build up on the right end. So the right end is going to end up at high potential. And our left end would be at a lower potential. That would be our negative end. We'd have a potential difference delta V over the two ends of that inductor. Okay, so that was a quick recap, like what we did on the previous slide. However, now our current is decreasing. Let's put it in terms of the equation. Delta V, potential difference across the ends of the inductor, is minus L times di dt. If we decrease our current, then di by dt is negative. And if di by dt is negative, then it says that the induced potential, delta V, gets bigger as we move with the current. Okay, now hopefully you could follow along with that part if you understood what happened with the increasing current on the previous part. Let's use the ideas we've talked about so far and try and answer what I think is a bit of a nifty question. Maybe you've observed this before. If you haven't, then by all means try it out and see if you can see it now. If your computer is plugged in and turned on and you unplug it, you probably will see a spark jump from the plug to the outlet. And it's not just your computer, it can happen with an iron or a toaster or a TV, anything at all. So why don't you try that out, see if you can see the spark, and then we'll talk about why that happens. So to explain that effect, let's start with the idea that if our switch is closed, then this simple circuit represents our plugged-in computer. And if we open the switch, this is when we unplug. So now what happens if we just unplug the computer? Let's remember that the induced potential across the two ends, so delta V, is equal to minus L di by dt. So a potential induced is going to be the inductance times the change in current over the change in time. Delta V is going to be very big if the current changes fast, like flipping a switch. So delta T is small because it doesn't take us very long to unplug it. And our change in current is also pretty big because our resistance is going to be pretty small. So what we end up getting is a very big potential difference across the inductor. And if we get a big potential difference across the inductor, we're also going to get a big potential difference across the gap between the wall and the plug. So for that delta V across the gap, let's remember that our electric field is delta V over delta X. That gap is pretty small. There's only a few millimeters when you first unplug it. Delta V is small, or delta X is small. Delta V is big. That makes our electric field really big. And what happens when you get a big electric field across a small gap of air is you get a dielectric breakdown and current flows across the air. And that's what makes a spark when you unplug things. So when you unplug it, you're changing the current really rapidly. It makes a big potential difference across the inductor, which makes a big potential difference across the other circuit element, which is the gap between the wall and the plug. That big potential difference over a small distance makes a big field, which makes a spark across the 2 points. For what it's worth, that's kind of how spark plugs work in cars as well. Let's do an example now. Say that the maximum allowable potential difference across a 200 millihenry, so that's our inductance, is 200 millihenries, is 400 volts. So delta V across the ends is 400 volts. You need to raise the current through the inductor from 1 amp to 3 amps. So the initial current is 1 amp. The final current is 3 amps. How long can you take without blowing the inductor? So let's see. Let's apply what we know about the induced potential across the ends. So delta V L is equal to minus L di dt. This is the form we'll use when we have a smooth change in current or a function for our current. If we have two discrete points, then we can say delta I over delta t. So let's use this expression. It doesn't matter which end has the higher potential. So delta V across the two ends, the magnitude is what we're interested in, is L times delta I over delta t. Okay, what is our delta I? That's our change in current. Delta I is I final minus I initial. 3 amps take away 1 amp equals 2 amps. Okay, everything in our expression here is positive. So we can say delta V is L times delta I over delta t. You can solve for delta t equals L times delta I over delta V. Let's put in our numbers. So we've got 200 millihenries times our change in current, which is 2 amps, divided by our maximum potential that we're allowed to have, 400 volts. And what we get is 0.001 seconds. Okay, so that's kind of a long time in terms of current. Let's do one more example now. The current through an inductor with an inductance L is given by I equals IO times sine omega t. So our I is a variable. Find an expression for the potential difference across the ends of the inductor, and then do some plug and chug numbers to find our I0. Okay, part A. We remember that delta V across the ends of the inductor is minus L times di by dt. So we'll fill in our expression for I, d by dt, of IO sine omega t. Okay then, so we have to do the derivative of sine omega t. We get minus L, we take our IO out front, and d by dt of sine omega t. The derivative of sine is cosine, so we get minus L times I0 times omega times cosine omega t. So there's our expression for the potential difference across the inductor. Okay, part B says the maximum potential across the inductor is delta V equals 0.2 volts. When we know that our L is 50 microhenries, our frequency is 50 kilohertz, what is our maximum current I.O.? Okay, so we have some numbers we can plug in. Let's start with our expression for delta V because we know what the maximum potential is. So delta V L equals delta VL maximum. So delta V is a maximum if cosine omega t is equal to minus 1. And that's because cosine can range between negative 1 and plus 1. So if my cosine term is equal to negative 1, I get delta V is equal to minus L times IO times omega times negative 1, which means that my delta V is equal to I times, wait, sorry, got mixed up with my symbols there. Delta V is equal to L times I0 times omega. So that's my maximum potential. That's the biggest the potential can be. Okay, so now I have some numbers I can fill in there. So 0.20 volts is equal to the inductance, 50 microhenries, 50 times 10 to the minus 6 henries, times I0. Okay, now a little bit of a hiccup. We have omega, but we're given frequency. So we'll have to remember omega equals 2 pi f. So times 2 times pi times 500, a kilohertz is times 10 to the 3 hertz. And then we can solve for our I0 equals 0.00127 amps. So that's that maximum current value. Here's a problem for you to try as a homework problem. It's not that complex, so I won't do it as a video, but I will write up and post the solutions.